here's the problem from the previous video. There's one more twist I want to add on to it. And in this section I feel like just keep on throwing twist and twist and twist. So the twist in the previous video was we weren't rotating around the x-axis, we were rotating around y is equal to minus 3. Well, now I'm going to change this. So this isn't y is equal to minus 3. This is going to be y is equal to, let's say, 7. And so what difference does that make? So before, this is what we were rotating around. Now this is what we're going to be rotating around. Okay, so this picture is getting pretty messy. So let's redraw this. But I'm using the same problem so we can kind of share some of the work that we did before. So what do we have? Okay, so set of axes, and here is y is equal to x squared plus 2, and here is y is equal to 4 minus x squared, and now we are rotating around y is equal to 7. And we are, of course, rotating the same region as before. Now we're going to use the same exact formula, and we already did the work of, in the previous problem, we know that a and b here is minus 1 and 1. So let's see, this is giving us v is pi times integral from minus 1 to 1 of stuff for us to fill in. And now the tricky thing is, what is our outer radius and what is our inner radius? Well, when we think about this, we might say, oh, this red one, the y is equal to 4x squared, that is the bigger one, that's our outer radius. But things change now that we're rotating about an axis that is above our region, not below our region. So our outer radius is actually going to be x squared plus 2, the distance from x squared plus 2 to y is equal to 7. The inner radius is the distance from 4 minus x squared to 7. So now, so this is the first big thing, is realizing that this is the outer radius and this is the inner radius. If you got these backwards, if you flip-flop those and you calculate everything out to the very end, you should end up then with a negative volume, and of course that's very undesirable. Volume should be positive, not negative. Okay, so what do we have to do now? Now we have to figure out what is the outer radius now. And so to figure out this outer radius, how can we do that? Well, this outer radius, it's going to be 7 minus this chunk down here, which was the original x squared plus 2. So the outer radius is 7 minus x squared plus 2, so that's 5 minus x squared. As for the inner radius, so this little chunk here is 7 minus 4 minus x squared. And so that ends up as 3 plus x squared. And so now putting these pieces together, so the outer radius is 5 minus x squared, all of that squared, minus 3 plus x squared, all of that squared. And so just as in the previous problem, you can crunch it out if you want to. I'm not going to crunch it out because I want to focus on the setup. Once again, the setup is what's important here. And so there's two nuances. The first nuance is realizing that the roles of the in and out have flip-flopped in this problem from previously. And the second nuance is being able to come up with exactly what this distance is. It's not just add 3 like we had in the previous problem. It's a little bit more subtle of a calculation. Okay, so to kind of wrap up this problem and the previous one, here's our second pre-class problem. So I want you to set up integrals. You don't need to evaluate them. I just want you to write them down for the volumes obtained when the region R, which is bounded by those four curves there, is rotated around y is equal to -4 and y is equal to 12. And so you should see one of them, the axis is below where you're rotating around, the other one, the axis is above where you're rotating around.